Mic's working? Okay. Thank you for the wonderful introduction. As you may have heard from my introduction, I come from a software development background. And today I want to talk a little bit about tech, and specifically why tech is a designer's best friend. I will warn you, there is a little bit of code that is going to show up in this presentation. Do not be afraid. I'll make sure it's all fine. You'll be just fine. Don't worry about it. So, as designers, it used to be that we could pick up a sketchbook and create. Our craft was about taking a fantastical concept born from countless hours of research and introspection and then rendering it. This is Sid Mead's vision of the future, personal transportation, circa 1970. This is what was created. Today, this is no longer enough. 9 times out of 10, the designs that we create involve an experience, and that experience will most likely involve tech. It is far more about the experience and the form together than the form alone, which means we must make. The challenge is that software development and electronics, they're seen as engineering or science. They're not approachable. They're treated as dangerous areas with rules that can't be broken. The truth is that it is just as safe to tinker with electronics or code as it is to pick up an X-Acto blade and cut into a piece of foam core. The good news is there's hope. Maker movement is upon us. Even President Obama is excited. Make Magazine, Instructables, Hackaday, all of these places are starting to demystify tech. They have articles on 3D printing, sensor integration, and they're even doing some really advanced integration around home automation. The challenge is with most of these articles, they're a recipe. They're a description of how to recreate what someone else has already done. And as designers, we're typically trying to create something that no one has ever seen before. So that recipe starts to introduce its own set of problems. So let's take bread, for example. Imagine you don't know anything about baking. That's something I don't know anything about baking, so this is easy for me. If you see an ingredients list like this, along with a set of, let's say, 20 instructions, you would be hard-pressed to figure out which change you would need to make a crust thicker. The ingredients are there. You can recreate the loaf, but you don't understand how the individual piece parts work together. The same is true with code. Don't worry, it'll be fine. If you wanted to take this formula, this is a standard block of code, and you wanted to figure out how instead of doing decimeters into tens of feet, you went decimeters into yards, well, the formula is there. All of the components that you would need to rearrange this formula to get to yards instead of tens of feet, they're all present. But you don't understand why this works. None of the breakdown is there to help you disassemble it and build it into something new. Today, I want to demystify the process of reverse engineering a recipe. And to do that, I want to talk about some of the tools that we use in our studio to do that. And I want to do that in the context of one of the projects that we did last year called the Denny bike. And specifically, we're going to talk about how we got the turn signals to run. So for those of you who haven't seen Denny, this is the Denny bike. This was a competition that we entered through the Oregon Manifest, along with design partners from five cities. So we had firms from Chicago, Portland, San Francisco, and New York. We created a Denny bike specifically for Seattle, and the goal of this project was to entice drivers, people who don't normally cycle, out of their cars. So this bike was built with a series of features that make it the perfect urban bicycle for Seattle. And part of those were 3 technical systems. The first was lighting. You can kind of see it in this photo. We have turn signals at the front. We have a little halo light at the front for additional visibility. We have a full-on headlight. There's a brake light that you'll see in a future slide. We then had an automatic shifting system that's on the rear hub. That system was designed so that you are always in the power band. You don't have to worry about what gear you need to get in and think about it. You just get on the bike and ride. It takes care of all that for you. And last but not least, for any of you who have been to Seattle, we had an e-assist motor around the front hub to help you get up hills. So lots of tech in what seems like a simple bike. We're going to talk specifically about the turn signals, something that should be very simple. From a design perspective, this was very easy. Physically, we put them as far front on the bike as we could, and we put them out to the far left and right edges. Done. No issues. Then we had the simple challenge of making them blink. This couldn't be easier. You have a single button, you press the button, the light turns on, and then it turns back off. It's not quite that simple. Before the light could blink, we had this concept of ambient light. All of those lights that you saw on the bike stay on if it's dark out to give the rider a bigger presence on the street. And so that varying light level needed to be controlled. We got a sensor from a company called Adafruit. They have a wonderful tutorial. This is actually the wiring diagram from that tutorial. And it explains specifically how you hook up that sensor, which is the little block that you see right here, read the ambient light level, and raise or lower the intensity of an LED. Couldn't be easier. The recipe was dead simple, and it worked great. We plugged it in. All the lights on the bikes lit up and changed as I covered it or hit it with my iPhone. It got brighter or darker, depending. So it was wonderful. This is a shot of the turn signal there on the front of the bike. What it turns out that we had done, though, by getting the ambient lights to work is that we had been short-sighted in our concept. Funny thing, if you set the light level to go up and down and then you need the light to blink, a blink is the effect of a light going all the way down and then all the way back up. Well, we already set an ambient light level that set the light level at a specific level, so if you want it to go all the way down and then all the way back up, you end up interfering with that. So we had to go back and look at the whole lighting system together, not just turn signals. We also had to look at brake lights and so on. So we had the ambient light level that we talked about. That ambient light level became even more complicated because there are different colors of LEDs on the bike. And these are not just normal fixed LEDs with a single color. We used RGB LEDs called NeoPixels. If you haven't used them before, look them up on the web. They're outstanding and a whole lot of fun. They can create 256 colors, each of them. And we had a set for the turn signals that were set to yellow. The set for the front were set to white. The brake lights were set to red. We had to figure out the color and intensity. We wanted the brake light to be brighter than the front light, so that had a different intensity. We had to manage all of that. Then we had to figure out how to cycle that intensity from a value of 0 to 233. The turn signal, we originally started with on and then off. Didn't look very good, kind of ugly. So as designers, we wanted it to look pretty. So we had it cycle on and off. It was pulsing. If any of you have seen the old MacBooks with the sleeping light, that sort of effect. Absolutely beautiful, worked great. But when we got to the brake light needed to strobe. We wanted it to really grab somebody's attention. And as it turns out, if you set a group of logic to slowly cycle a light on and off, you introduce a wait state that conflicts with another light that you want to go really, really fast. So it would go on for the turn signal, strobe for the brake, wait, on for the turn signal, on for the brake, wait. It was a mess. Kind of showing you how the sausage is made, so bear with me here. Then we had to figure out left turn signal versus right turn signal. So if I turn on the turn signal for the left and it starts pulsing beautifully, we love that, and then we hit the button to go for the right, the left stayed blinking and the right turned on. Well, there's new logic that we needed to introduce because these aren't hazard lights, they're turn signals, so when one goes on, the other one should go off. All of this logic had to be considered. And then last but not least, the elephant in the room, we had to figure out how to make this thing auto-shift at the same time. All of these features, all of these lighting controls were all going through the same microcontroller. So the code that we created had to be able to bring all of these things together, which means understanding and looking at them as a whole. Getting back to that loaf of bread, it's not just about the ingredients, it's how those ingredients go together. We had tested all of these ingredients separately. We had made the light pulse beautifully. We'd made the brake strobe perfectly. We'd gotten exactly the color of yellow that we wanted on the edges for the turn signals. And we even had the auto shifting working great, but we hadn't brought them all together to make that loaf of bread. So what I want to talk about today is the tools that we use to bring all of these things together, because that is really what changes technology. And the most important thing that we learned when you're taking each of these ingredients together to make that loaf of bread is that you have to make your technology visible. Unlike a piece of foam core or modeling equipment or even a 3D printer, you can't see what a microprocessor is doing readily. You can't just look at it and know what data it's trying to send to something else. The same thing is true if you're looking at a bit of code. Unless you're a developer, when you look at that code, and even if you are a developer, if you look at one section of code, it's really hard to tell what just the rest of it does when it's all put together. So I want to talk about a few things that we've found that help us adopt and consume new technology. Because as designers, we're constantly trying to push the envelope, and you're not always going to be working with things you're comfortable with. The first of these should seem really straightforward and easy. But I will tell you, every single electrical engineer that I know has broken this rule at one point in their career and have cursed themselves for it. And that is label your wires. When you start to hook something up, even if you only have 2 wires, label them. Put a piece of sticky tape on them. Do something so that you know where you're at. Because by the time you're done, it will probably look something like this rat's nest. Or you'll have something like, oh, there's only 1 orange wire, and I know the orange wire is signal. And then, lo and behold, 2 weeks later, there's a second orange wire, and you have no idea what that one does. And you can't remember if it was the left one or the right one that made the signal work. So taking a couple seconds, a little piece of tape, wrapping it around your wire will make a huge difference. And if you remember that slide from a couple pieces back when you saw the Denny bike on the bench, there were a lot of wires in there. And when I started, none of them had labels. The next thing that I want to talk about is source control. This is code. Bear with you. You don't need to read any of it. I'm just going to talk about the red and green colors here in a second. There is a magical, mystical tool called version control. There are lots of different types of version control. GitHub is one of the main ones that we use internally, but there's Subversion, Mercurial, etc. These are time machines for code. They are the ultimate undo. If you are working on any project and you've assumed code from someone, anyone, it doesn't matter where it's from, load it into a version control system. If anything goes wrong, it can take you back into any point in time. You check your stuff in, and you can see specifically. So if you look at the red blocks and the green blocks here, the green blocks is what's there now. The red block is what was there the last time this code was checked in. This gives you an absolute ability to go back and compare. And you don't have to remember where you left off. The computer takes care of all of that for you. So if you knew something was working 2 weeks ago, you can go back to where you were 2 weeks ago, restore the code exactly the way it was, and figure out where you left off. This has saved our bacon on more than one account. This is like labels for code. The next thing is a bit more challenging. We talked about a little bit about microchips and how you can't tell what you're thinking. These 2 devices, this is an oscilloscope and a logic analyzer, can tell you specifically what that chip does. And the reason that I bring these up here and show you on screen is that most people will look at these tools and think, I have to be an electrical engineer to use these things. These are massively complicated. This is not a simple touch screen. There's a whole bunch of buttons up there. There's little BNC connectors. I have no idea what plugs into those. This is a complicated thing. I would like to draw your attention to the 3rd button from the left-hand side in. It says Auto. There's a magical thing on every single computer chip unless it comes from the Apple Computer Corporation. They will have a label on it that has a part number and a manufacturer. If you plug that information into Google, you will find a pinout of exactly what that chip does. It will describe it, it will tell you what comes in, what comes out, and it will tell you specifically where to plug in probes from these guys to read the data that's coming off of it. Sometimes I think that this is a little trick that EEs don't tell people, but I'm sharing it with all of you, so here you go. These aren't very expensive tools, by the way. That logic analyzer right there, the 16 is kind of expensive. It's like $500. This oscilloscope here is less than $1,000. You can get a cheap logic analyzer for like $200. It plugs into your USB port, and it gives you everything that you see there on screen. Now, that screen may seem a little bit daunting. If you look at the blue line at the bottom, most of the chips that you're going to deal with, when you look them up in Google, they're going to have some sort of communication protocol on them. They'll say something like serial or I2C or SPI or CAN. Those are descriptions of a specific way that that chip talks to other chips. Well, if you take one of these logic probes and you look at that blue line, the high part of that line represents a 1, the low part of that line represents a 0. The good news is for all of us is that if you plug a logic analyzer into that and you tell it that that's speaking CAN, for example, you will see real text. You don't need to convert from binary. You don't need to convert from hex. It will do it for you. And you can sit there and listen as that microchip talks to your other microchips, and you will know specifically what they are talking about and be able to debug it. It demystifies the data going between those 2. We talked earlier about version control. One of the other really cool things that you can do in your code is comment your code. For those of you who have never developed anything before, a comment is a short description of what it is your code should do. This is just an example that I used from The Shining. The idea here is that you put in a block that the computer doesn't read. This is for you as a developer, as a creator, to describe what it is you're trying to do. I encourage our developers to write a comment before they ever write their code. They write it out like you would write the outline for a proposal or a presentation. You say this block of code is going to do X, and then you write the code underneath it. You do the same as you move through. The great news is that this same content gets uploaded into that version control system, so you can go back to this and see what you were thinking at a time, and you can compare that to the code that you created and go back and forth. It is an awesome set of labeling that you can do in your code, and it will really help you as you go through. Along with the comments, you can create debug statements. This is an actual block of code from the Denny bike. This is the block that we use to call the right turn signal. The piece that you see highlighted there is a debug statement that I put in. So as we were going through and testing these, as we talked about all of those ingredients and knowing that they worked, well, we'd test them all individually on the bench, but when we start to put them together, you start to have doubts. Well, did the button work? Is the light dead? Did the logic controller not get it? You have to think about all of those piece parts independently. A simple debug statement like this is a serial line, will output it to a console while you're working on your bike, and you will know that the microcontroller received the signal from the button and is trying to flash the light. So if the light isn't flashing, odds are it's not the button, it's not the microcontroller, check your LEDs. This is one example. There are multiple ways to do this, and every single coding language has some ability to do a debug statement. The more that you put in there, the better, especially for designers. It's a little bit challenging. If you go out on the web and you look at dev tutorials and things like that, they're going to talk to you about, they're not going to put many of these statements in. You'll start with some debug statements, and then they'll tell you to take them all out. As designers, don't take them out. You're going to need to go back here. You could pick up this project 2 years ago. You aren't building things for production. Put it in there. It'll help you. It'll give you that visibility. Last piece that I want to talk about as a tool is a dirty little secret. As Russell mentioned, I have been in the software development world for 20 years, and some of the best developers I know, those guys that have been around far longer than I have, and even the real hotshots that think that MIT are a bunch of school children, every last one of them Googles their code. I come up to them and I say, hey, you know, I have this new thing and I want to have some JavaScript to make this thing spin around. And they're like, oh yeah, let me Google it. They don't sit down and they don't start writing it. They'll go and find out if someone else has done it before. It is absolutely totally fine to beg, borrow, or steal code from anyone else. If they've put it on the internet, it's fair game. Go for it. Try it out. There are licenses. You can figure that out later. But if you're trying to build something, and hack it together, take what you can find. But take the time to really break it apart and make it your own. Don't just accept that it works like I did when we were looking at that ambient light sensor. Understand how all the pieces and parts work. Use your version control system to give you that safe haven to fall back to and make it work exactly the way you saw in the recipe, but break that recipe apart and figure it out. There is no shame, there is no stigma about using Google. All the best developers I know do it. It's kind of like calling your mom when the bread doesn't turn out quite right. So hopefully I've made all of you freed up to go and do and integrate any piece of tech. I did this presentation primarily because the tech that we integrate changes all the time. So these are tools that you can use all the time. Walter Darwin Teague said, for the first time in history, the possibility of a good life for all men is conditioned only by our own discretion and intellectual ordering of our affairs, our energy and acumen in utilizing the tools we possess, and our goodwill in defining our objectives. This is the job of design. Tech is just another tool. You can integrate it into any of your experiences and change the world. I hope this presentation has given you new tools that let you push tech and imagine great things. Thank you very much.